So today I'll introduce my lab. It's been a little over 2 years, and it's a sort of, uh, in a way, it's a summary of what we do, as well as some of the concepts which we have been looking at. Okay, so the lab basically looks at two important things, which is topological materials and superconductivity in high TC materials. But here we are looking at high TC as devices and not really high TC superconductivity itself. So, but something which interests us the most is if we combine topological materials and magnetism and superconductivity, what happens at the interface? We don't really do exactly what's here, but we try to grow materials epitaxially and ask the question, what is it that happens at the interface in an emergent phenomenon? So, one of the things is looking at magnetic topological insulators, where you see that the quantized conductivity is close to E square over H values, and this is barely at 4 Kelvin. So that's one of the things. And a lot has been spoken about altermagnets. We grow them using MBE, and one of the materials we are looking at is MNTE. And the most important part is that you get very curvature driven anomalous Hall conductivity in these materials, and we do these as well. And something close to our hearts is looking at what happens when you bring materials together. So here is a magnetic insulator. You can see the magnetization as a function of externally applied magnetic field, and then there is a normal metal on top, but you see that the anomalous Hall resistivity picks up a magnetic signature just by being in proximity. And why so, and so on, and engineering new such material interfaces is our thing. And lastly, our favorite is also looking at BISCO, where we look at high TC superconducting devices. And this is one of the devices where we see quite high TC, and we are trying to engineer superconducting diodes, Josephson junctions, and trying to make a quantum circuit out of it. By that I mean squids and Josephson junction related ones, and not really anywhere into higher frequency domain. Yeah. So this is what we are doing, and I only take the credit, but it's these people who do all the work. So thanks to the group, which has been really hardworking all the time. Yeah. So that was a brief overview of what we do, but most importantly, today's discussion will be on something along these lines, but it will be about engineering Rashba spin orbit coupling in all metallic Josephson junctions. Okay, so something like this is quite familiar to this audience, I believe, because of the kind of talks that have already been given. Here you see basically something called a magnetic interference pattern, where critical current oscillates as a function of applied external magnetic field, and this is in indium arsenide. Okay, and when you have such high mobility, high electron mobility systems, it's quite relatively simpler to make Josephson junctions, given that the electron mobility is pretty large and there is no much of scattering in the weak link itself. So, but there is a catch. If you try and go to 3,5 semiconducting materials all the time, indium arsenide or any such interface like gas and so on, you need an MBE to actually make these interfaces, and you actually need really high infrastructure to do all of this. So maybe not many will actually pursue this path, maybe not, but things will become much simpler if metallic systems displayed this property. But there is a catch, that metallic systems have very small mean free path, because of which you need to make the weak link length really very small, and this is a nanofab challenge. So nature is unkind that way. Okay, and we thought, okay, can we look into these all metallic systems and try to look at Josephson diode effect in these all metallic systems and engineer the Rashba spin orbit coupling. Can we do something about it? That was the whole point, because you have Rashba spin orbit coupling in indium arsenide. So can we just engineer the metallic system such that we get Rashba spin orbit coupling parameters of that order? Is that possible? So this work was done in collaboration with the group of Professor Christoph Strong, and Maximilian was instrumental in doing many experiments. So what are we looking at? We are looking at something like this, which was the inspiration. Where you see this blue patch here is nothing but indium arsenide, on which there is a series of aluminum strips that are drawn, which is basically a Josephson junction array. Okay, and in this large spin-orbit material interface, if you apply an in-plane magnetic field, because of magnetochiral anisotropy, you get the positive critical current and the negative critical current splitting this way, giving rise to a finite diode, Josephson diode effect. That's the word for it, right? Now, this was quite well understood theoretically from this paper, where they really modeled what happens to the magnetochiral anisotropy when you have such large spin-orbit coupling systems in place. So these two papers basically summed it up and sort of led the way for Josephson diode effect. Fine? Okay, but again, we are still in the indium arsenide level. But the key is Rashba spin-orbit coupling here as well. Now, what we looked at was something really different. We said let's look at gallium arsenide and this really complex stacks. But you may now rise up and say, hey, look, you also have a 3-5 semiconductor which is gallium arsenide here. But it is not really so, in the sense that gallium arsenide is just a substrate. We are not growing gallium arsenide on gallium arsenide or something like that. But we are putting a very small layer of iron, aluminum, platinum, niobium, and so on. Okay. There is a very specific reason for choosing such a complex interface. Iron on gallium arsenide exhibits in-plane uniaxial magnetic anisotropy. By that I mean it prefers a magnetization vector in the plane of the sample. So we were about to study, can we rotate the magnetization vector in the Josephson junction weak link and study this. Whereas platinum here is for really interesting reasons. It has bulk spin-orbit coupling, but at the same time you can etch down niobium and stop exactly at platinum. It really helps a big time in fab process itself. Alright, now you may say, hey, you already have this multi-layer complex Josephson junction. Can you do something simpler so that I can believe your results? Sure. We did silicon oxide, where we completely remove the spin-orbit coupling from the picture, which comes from gallium arsenide ion kind of things. And then we also do something very simple, which is silicon oxide copper, which is believed to have negligible spin-orbit coupling overall. Fine. So let us study all of this. Our experiment is really very, very simple. Pass current and measure voltage. So we pass current this way and measure voltage. Okay. And the first thing is you have to look at resistance as a function of temperature. You see that superconductivity begins here at the electrodes, and here the Josephson junction is superconducting. I just want to underscore here at the point that this is an SNS Josephson junction. It's not a canonical Josephson junction like an SIS. This behaves very differently compared to SIS kind of things. Here we are looking at wave function overlap integrals rather than tunneling. Okay, so IV curve is another thing that you want to look at. You increase current and then suddenly there is a voltage drop, and that is the critical current. But if you squint your eyes a bit, you will see that there is a non-reciprocity here. Let me make it slightly clearer by, look at this now. So I apply an in-plane magnetic field, which is in the 200 millitesla magnetic field. If I apply it in the plus 90 degree or minus 90 degree, I am basically changing the sign of the magnetic field. And you see here that the green is ahead of red, and here red is ahead of green. Yeah, and that marks for your Josephson junction diode effect. It's nice to see that you have a positive critical current splitting nicely when you have this red and blue. But there is another additional thing, that when you apply magnetic field along these directions, you also have to take care which is the direction in which you sweep the magnetic field, and that's where a lot of what was discussed before in the context of vortex physics comes into play. I'll explain this very shortly. But if you see here, eta, which is this Josephson diode factor, basically for the plus 90 degrees here, minus 90 degrees here, that indicates very clearly that you have magnetochiral anisotropy. you change from plus 90 degree. So 90 degree basically means you have current perpendicular to the junction, and then you go minus 90 degree, you have perpendicular going in the other direction. So you see for any other direction, it smoothly sweeps through. And this is a hallmark of magnetochiral anisotropy arising from interfacial Rashba spin-orbit coupling. And this is engineered by having this sort of multi-layer metallic systems. It has nothing to do with any of the other things, but it is engineered Rashba system. I will slightly switch gears now to actually see, it's slightly easier to visualize that instead of looking at as a function of magnetic field, let's look at it as a function of angle. Yeah, if you see it as a function of angle, then you see that the diode efficiency has to sort of cross at 0 degree, and that's what happens here. Now this is diode efficiency when you have iron, aluminum, platinum, this heterostructure, but when you have something like copper, platinum, there is crossing, but it is a little weaker and hodgepodge in a way. But if you see the numbers, it's much lesser. Fine. And then if you go to completely copper junction, there is absolutely no crossing whatsoever. So you can actually see that interfacial Rashba spin-orbit coupling is actually playing a role here in tuning diode efficiency very significantly. Okay. So there is another thing I want to emphasize here. So we have looked at it so far by applying an in-plane magnetic field. Let's apply an out-of-plane magnetic field. What you expect is a nice Fraunhofer magnetic interference pattern. Yeah, but in a copper-platinum junction, we ended up seeing things like this, jumps. Yeah, and jumps is a word today if you're awake in 2 talks before, right? And it is exactly the same reason that there are sporadic vortex jumps that happen here, and if you end up correcting for all those jumps yourself, then you will see that there is a Fraunhofer hidden behind these jumps. Okay, but very importantly, these Fraunhofer interference patterns are shifted. That is, if I'm moving from right to left, then here is the junction, whereas if I'm moving from left to right, here is the maximum, right? So it has shifted from its 0, and one has to really understand why is this shift so. And this kind of shift has been actually attributed to quite a few exotic things, beginning with phase batteries, spin triplet, and whatnot. If you actually look at literature, the moment there is some phase shift in the Josephson junction, it has been associated with really big names like spin triplet, superconductivity, and so on. So obviously it doesn't really make sense just because that you have a phase shift, that too in the wrong direction. If you see here, right, you come from the right, from the left. If you have it on the right, the dip, then it's a ferromagnetic hysteresis and you can associate it with triplet superconductivity. Whereas here you have the dip happening in the same direction even before crossing the field. So this was a challenge, and it took us quite a while to actually understand, and the answer lied in the Bible of superconductivity. So we, especially me, we believe that this is kind of the Bible because it was written in 1990s if I'm not wrong, but it covers a lot of concepts including devices even to this present times. So what does it mean? So if you go back to the chapter on vortices and vortex flow, you will see this something called the critical state model, where you apply magnetic field along this direction, that is you go from 0 to increasing direction, then you're basically applying a magnetic field here, but then what the junction sees is a much lower field than what you apply, and that comes purely because you have vortices. I'll quickly show this, okay? And you go back, then there are trapped vortices in there. They will give rise to something else. So how do we understand that here? So let's try this, okay? So you apply a magnetic field, external magnetic field which lies here, and you think that this is the magnetic field you apply, and you are here. Fine, you have broken the critical state and critical field, and this is where you are. Now, you start sweeping back, fine, but the effective magnetic field seen is much lower because of the slope that this induces at the edges, fine. And if you actually write down the direction of current, magnetic field in the left junction and the right junction and so on in the vortex flow, you can actually get this del cross B is mu naught J sort of physics to see that the actual magnetic field seen by the junction is much lower, okay? And what happens is you keep on doing this process, and then if you come here, you see that you're sitting here at zero magnetic field technically in the superconducting magnet that you have, but you actually have trapped vortices which have exactly negative field of some magnitude. So overall field seen is zero, fine, and that can give rise to a maxima in the Fraunhofer interference way before you cross zero. Okay, so that is one thing. And lastly, let me throw this question at you. So what is the meaning of time reversal symmetry? Fine. And if you see, if I have a point here, okay, which corresponds to minus I minus B kind of a point, then its time reversal symmetry partner should be simply here, because I change I minus B to plus I plus B, right? But in situations where you basically have this critical state model dominating, you don't see this at all. Like you have a feature here, you don't see this here at all, right? But it is found here. And what is the difference between the top and the bottom? It is that in the top, you are moving from left to right, whereas in the bottom, you are moving from right to left. Okay, so there is a time reversal symmetry partner for each of them in a vortex flow dominated Josephson junction if you do three operations, and those three operations are plus I plus B, you change the direction of current, change the direction of magnetic field, but also change the direction in which you sweep the magnetic field. So these three things become important, and somehow in the community, I haven't seen this happening much, or manual offset of simply the maximum is followed. But one has to understand that it can all be modeled and related to the critical state model. So just to show that, I have shown you here that there is this violet curve and there is this sea green curve, right? They overlap perfectly, and this blue and the orange curve they overlap perfectly. But if you take any other combination of critical current curves, they just don't overlap at all. Okay, so these were the three things that I wanted to say, that there is a Josephson diode effect in all metallic systems. If you carefully engineer the interfaces, you can get really high Josephson diode effect coefficient, and critical state model is quite important in considering these all metallic systems. And time reversal symmetry partner finding exercise requires one more step in these junctions. So thank you very much for your attention, and apologies for the beginning. Yeah.
Okay, thanks Sarala for this time slot. The session is open for questions.
Yeah, so regarding the vortex traps,
Right.
a easy way maybe to check for it would be like just to heat up the junction.
Yeah, these don't go. These don't go away.
No, like if you heat up above the superconducting transition and then cool down without any current and
Right.
at like superconducting magnet staying at zero,
Right.
it should be able to get rid of it.
Those correspond to the vortex jumps that you see perhaps. But if you want to get rid of this phase completely, then just warming up and cooling down doesn't help, to an extent that we even warmed up the entire cryostat, not just the sample, including the superconducting magnet was warmed up. Okay, and then the first measurement shows this. So it really, it was an experiment spread over years to check everything, and it was really the vortex trapped in the Josephson junction the moment you apply a finite magnetic field. It doesn't really help warming up the junction.
So in that case, that should be a very what would I say? It would be a very it would not be very deterministic, right? Like the vortex can get trapped anywhere, and you can.
So this
get
is deterministic. That's the whole idea. Because so this is very very deterministic. It's not something like a sporadic jump. For example, I just want to make it clear. So when you apply out of plane magnetic field, these are very random, like you said. These correspond to those. But one second. So these ones, the shift that you see entirely, that not at all. So it depends on what sort of pinning you have perhaps.
Thank you.
Your diode efficiency, you showed peaks at a certain point of 10% at around 250 millitesla. Around that, it again drops.
Right.
Why does that happen?
Again, vortex flow is the.
And often the diode effect, of course, has many reasons for.
Yeah.
And vortices, in fact, are also responsible for creating this asymmetry in JCs.
That's correct.
So, do you think there is also an effect of vortices which is playing a role when you are looking at this diode?
Right. So, it's actually a very good question. In fact, a lot of careful experimentation is required to eliminate or rule out the role of vortices in this. Yeah. But here, in this curve, this is a magnetic field applied in the plane of it. So there is no role of and what you're saying is right in the sense that even a one Oersted field is enough to cause this. So a careful alignment is necessary. The way we did this was to have a strip of aluminum whose critical field is low and then, really align with respect to that.
Okay.
Yeah.
Can one think of doing some changes in the device design to engineer this vortex pinning feature in the Fraunhofer like thing? You understand? So like you blamed it on this graded, right? There is a slope.
Yeah.
So if you extend that slope further,
Right.
How will it? It should affect it. Right?
So the way is if you make, see this is a planar Josephson junction where the two niobium electrodes are separated by about 15 to 20 nanometers. Now if you go farther, you may be able to do exactly what you are saying, but then the coherence length is really very, very small. So you can't go farther at all to get the Josephson current in first place. So in all metallic systems, length will not help, but will the width help? We didn't see any effect, although we work with many kinds of geometries.
So your critical current will probably go down if you make it a longer junction.
It will just go down very drastically. What I mean is, this is about 20 nanometer length. If we make it 25 nanometer length, that may not be even Josephson current. It's very tricky to fab these devices. So even to get a 20 nanometer junction takes many iterations.
I have seen papers where people make SNS junctions with 100 nanometer long.
Yeah, but 100 nanometer won't be Josephson junction with niobium and platinum all metal at all. You're right if it is, for example, graphene or
copper. I have seen.
Copper, yes, absolutely yes, because copper is a diamagnet and it is known to give a large coherence length and proximity with niobium, but not platinum or any other. If we want, copper doesn't have spin orbit coupling, so the whole idea is lost there, right?
It will be diffused, no?
Yes, long diffusivity, so that's entirely different.
It won't, first of all, superconduct if you go long with platinum.
Yes.
If it is copper, you may get a longer junction, but there is no spin orbit coupling.
You have critical current and normal current both flowing through.
In copper, yeah, but I mean the idea is to engineer spin orbit coupling, and if you don't have that, then there is no way.
Okay, so if there is no more questions, so let us thank Koala.